Okay, so SpinEcho. Sorry about the out of order lectures. So the earlier lecture assumed this lecture. So now let's talk about SpinEcho more slowly. so, so why, as I was saying in the idiom lecture, why echo? Why do we call it an echo? And it really comes from NMR guys just messing around with chemical samples. So they have an RF transmitter, they have an RF recorder, and so they just turn on the RF transmitter and they get a little signal, and then it just disappears. T2 star decay. If you don't do anything else, nothing happens. And then so we just turned on a little short RF pulse here at the very beginning, 100 microseconds, just a little boop, just a little hammer. And you get this signal that comes out, takes like about 1/10 of a second to disappear, and then nothing happens. But what if you just do a second pulse? So second pulse, if you just do a pulse, same thing happens. You get this signal that comes out and just disappears like that. And then what if you just do another pulse? So if you just do another pulse, you'll get a signal that comes out of that one. If it wasn't a 180, we'll talk about that later. So a signal comes out of that one. And then exactly this amount of time later, right here, you'll see this echo come up. And it looks like, and it's called an echo because if you just move this pulse over here, this guy sort of goes out. So this time is always exactly the same. The time from when the echo occurs is always exactly the spacing between the first and the second RF pulse. And so it's just a very, very concrete, observation. This big signal just comes out of no place. So that's an echo. That's why we call it sort of an echo of the RF pulse. And why do we talk about this? Well, virtually all the data that we record in MRI is in the form of an echo. We rarely record this initial response to the RF pulse. We're virtually always recording with an echo. There's like 3 different kinds of echoes. And we'll talk just about the SpinEcho today. So what are we going to do today is just look at a whole bunch of different time points in this picture here. So I'll draw out a good long picture here. So here's our initial FID like that. So that's our initial signal that comes out of the RF pulse. And here's the actual RF pulses. So the first one, we'll call it a 90-degree pulse. And so why would you often use a 90-degree pulse? Well, the 90-degree pulse would be the one that would give us the most transverse magnetization, because if we start lined up with the Z direction, there's no transverse magnetization, no signal, and then we do a 90-degree pulse that's the largest. If we did like a 45-degree pulse, we would get a little bit less transverse, so 90 would give us the biggest. So that would be how to get the biggest signal. And then what happens is we do another pulse, and if we do the second pulse as a 180-degree pulse, a 180-degree pulse is kind of like a special case, because if we started off lined up with the magnetic field, there would be no transverse magnetization, no XY magnetization. If we do exactly 180, now we're anti-aligned with the magnetic field. Also, no transverse magnetization. And so, if you do a really good 180 pulse, you could do sort of a sloppy 180 pulse, and there'd be a signal. But if you did a really good 180 pulse, there should be no signal come out. So this is RF stim, and this is RF, record or output. Record. So then what will happen is exactly this amount of time later, like over here, you're going to get the echo. And so here's our echo. So out of the blue, some signal will appear and then die away. And the amount of that echo, of the peak of the echo, is going to be described by this equation, e to the minus t over t2. So what are we doing now in terms of all our time points? So the first thing we'll do is I'll make, how many? 1, 2, 5 diagrams of the situation, sort of what we assume to be the local situation. And these 5 diagrams are going to be at point A down here. That's just after the pulse. So, or actually just before the pulse. So we'll make it just before the pulse. Yeah. So A is right before the pulse. Let me put an arrow so you can see it's before. Okay. So if we look at the situation right before the pulse, and then look at the situation right after the pulse, and then we look at a situation a little bit later, but there's still some signal. So there's the signal's decaying, but it's there's still some signal there. And then we'll look at a point here after the signal is completely decayed. So there's no signal coming out, but it turns out there's still some magnetization in there. And then we'll look at what's happening right after the pulse, right after the 180. So here's so this is basically no signal. This is we've decayed some. This is right after the pulse. This is right before the pulse. And then finally we'll look at what happens right here when the echo occurs. F. So the plan is try to understand what's the sort of molecular picture of what's actually going on in there. So starting off, we have 4. Okay, good. So I got about that much space. So if we start off, we've been in the magnet for a couple seconds, and so we're starting off at our equilibrium magnetization. So no transverse signal. So right before there'll be no RF signal because everybody's all aligned with the field. So this guy is T equals 0 minus, meaning right before the pulse. And then immediately after the pulse, if we did a perfect 90-degree pulse, we'd end up with this situation. So this guy would be t equals 0 plus, just after the pulse. So that's, so this is, time A right here, and this is time B. And it's supposed to be the same length as, I made it a little shorter, it didn't make it very good here. Let's make it, there we go, it's better. Okay, so that's the first picture. For A and B. So now what starts to happen? So two things are happening. So first of all, there's regular T2 decay because all these atoms are jostling each other and they're changing their magnetic fields locally, and that has the effect of very rapidly changing the B0, causing them to precess at different frequencies. And so that's the intrinsic decay because of all this local jostling in the magnetic field. Because if you've got a precessing proton, its magnetic field is changing, and so that's going to 123 millionths of a second change the magnetic field that this guy is feeling, and so it's going to slightly change the precession frequency of this guy, and so sooner or later the signal will all die away. That's the T2 part. But there's a second part, and the second part is, what if there's a static magnetic field difference? So for whatever reason, the distribution of atoms, there's slightly lower B field in one part of the sample than another part. But that B field doesn't change over time. So it's a fixed, like within a second, say, it's a fixed change. There's a slightly greater magnetization in this part than the other part, but it's fixed, it doesn't change. So if that happens, that's going to cause some additional tendency for the precessions to get out of phase, because if you're in a higher field part, you'll precess a little faster. And so now what we have to do, the way you sort of conceptually think of this is, if you were an MRI physicist, you would say we're considering different isochromats, but that's needlessly confusing. We have to sort of consider a bunch of different Bloch equations. That's the way you should think of it. So the Bloch equation has a particular B field, and so when you say, like, this is the change in the local magnetic field, and what's on the right side of the Bloch equation, there's a B field, the total B field. But if different parts of the sample have different B's, well, then you've got to actually have a second Bloch equation, or 1,000 Bloch equations for each of the slightly different B's. And so we'll just consider 2 Bloch equations. So now we've got a problem. So I'll draw it in 3D here now. So here's our z-axis up here, and the y-axis, and x coming out at you. So, and let's sort of imagine like a plane here. So imagine like the xy planes. That's the xy plane. So now what's going to happen is, let's do 2 Bloch equations. So here's one of the Bloch equations. So that's the magnetization for one of the Bloch equations. And say this is the amount of transverse magnetization. So why is that guy tilted up? Well, it's starting to get some T1 regrowth. So if you wait a couple seconds, it'll get all the way back up there. It started to lose some length in the XY direction. It looks about the same size, but imagine it's smaller. So that's just running the Bloch equation for one of these guys. And let's call this guy, frequency low. So that guy's, it's a little say it's a little higher, the B field was a little stronger, and so the frequency is a little higher than the average B field. And then let's have a second one that's even more high. So this guy is coming out at you a little bit more, and so this guy goes here, and so this one has its XY magnetization going like that. So this guy is slightly lower frequency, and this guy is a slightly higher frequency. So they're basically getting out of sync with each other. While at the same time sort of going back to the z-axis. So that's basically, point C. That's what's happening at point C. So at point C, the signal's starting to go away, but one of the things that's causing it to go away is the fact that these guys are getting out of sync with each other. And if they get out of sync with each other, when you add them all up, you get a smaller vector. So you can sort of think of this as, run 2 copies of block equation. So you got sort of 2 copies with 2 different B fields. Okay, that's point C. Now, what happens if we go all the way to point D? What will have happened is you'll essentially have gotten everybody completely messed up. So here I just put sort of X, Y, and Z, but now I made it 3D. So here's the X, Y, and Z. But what's going to happen now is you'll essentially have like a disk. You'll have a disk of vectors because everybody will have started to spread all the way around the circle. So basically they'll all be sort of starting to head back up to the z-axis, but if we wait long enough, they'll be all spread around this circle. And so what happens when that happens? Well, there's no signal. And they could even go 5 or 10 times around. Like if one guy, if this guy that was higher frequency would happen to be in a place with a relatively strong B field, it might get 5 or 10 cycles ahead of the other guys. And so they would just all spread into each other and cancel each other out. And so that's what's going on. That's what's going on at point D. So at point D, there's still a ton of local transverse magnetization left, but you can't see it because it's all completely dephased. They're pointing in different directions. Now, there's 2 situations you could have. You could have a situation like this where there's a lot of transverse magnetization, they're all pointing in different directions, then they cancel each other out. You can have another situation where there's no transverse magnetization like the one that we started with, if we waited a long time for all the transverse magnetization T2 decay to go away, then you would have no transverse magnetization. That also gives you a 0 signal. And so that's what so there's an invisible amount of transverse magnetization here. So that's point D, time point D. Okay, so now let's consider another, just for the illustrative purposes. Say instead of waiting until the transverse magnetization that we can record completely went away, what if we just moved the 180 further in? So where should I put that? I'll put it over here and erase it because I need this space for equations. So let's put it right here. So say we did something like this. Just the reason I'm doing this, you'll see why I'm doing this, so you can actually just get a geometrical picture of what's actually going on when we do the flip. So say we did the 90, and then before this thing decayed away, we did a 180. So when we look at the signal that we get out, we get this big signal out, and before the signal has died away, we do the 180. And then what's going to happen, the signal is still there, and at this point, you'll see an echo appear, like that. So there'd be a big signal at the beginning, but it isn't completely died away, and then an echo appears. Okay, so let's illustrate that situation. So that will be our flip situation. So we could just flip this, but it's harder to sort of see what's going on because everybody's pointing in different directions. So let's just flip these guys. So let's flip C. So this would be, point A here, which was before we did anything, and then point B right after we did something, and then point C after we started to get dephased. And now, before the signal goes to 0, before we get to this point, we're going to flip. So we'll flip C instead. So if we flip C, so let's put C right here, then what happens at E, sorry. What happens at E? So, right after we flipped. So that's right after, right before. Okay, so we'll flip this guy instead of flipping this guy, so we only have 2. So this would be, this is like run a zillion copies of the block equation, but that's kind of hard to visualize. So now let's just go back to our 2. So if we flip this guy, so what are we? What axis are we flipping around? So in this case, we flipped around the. Let me just write out the full axes. So this is the y and the x. So in this case, what we did is we flipped around the x-axis. We flipped it around the x-axis. In this case, we're going to flip it around the y-axis, just to make the drawing a little, maybe slightly easier to understand. Okay, so here's the y-axis. And what is a flip around a different axis? Remember we said that was just like a different phase of the RF pulse. Like you start the RF pulse to flip around the y-axis versus the x-axis. All you do is just start your transmitter 1/4 of a cycle later, and then you'll flip around a different axis. So now we've got this plane again here. So this is supposed to be the XY plane. XY plane. But this time what we did is we did a 180-degree flip around the y-axis. And what did we flip? We just flipped these 2 guys. So if they're sticking out, so they're sticking out at you, when you rotate them, just imagine sort of rotating them around 180 degrees around the y-axis. What are you going to get? Well, they're going to be underneath the plane, and they're going to be away. They're going to be away this direction. So let's try to draw that. So there'll be one that's sort of underneath the plane here, and another one that's underneath the plane here. We'll make that one stick out a little bit. So let me make that one stick out a little more for illustrative purposes. Okay, so those guys are going to be sort of pointing away from you because they had started to get ahead in this case, and so now they're going to be behind the y-axis. And if you look at where they sort of project on the xy plane, you can see that the one that was ahead is now behind. So that's fundamentally what the cause of the echo is. The cause of the echo is they're still precessing in the same direction. They're still precessing in the same direction around the z-axis, but when you popped them 180 degrees around, you'll cause the one that was the most ahead to be the most behind, and the one that was the most behind to be the most ahead. And so that's going to be, so this guy will be frequency high, and this guy is frequency low. So frequency low had been getting behind this guy. This guy had been getting behind this frequency low. F low here. So here's F low, but now we flipped him 180 degrees, and now he's in front of frequency high. And so what will happen? Well, frequency high is still frequency high, and so frequency high will eventually catch up to frequency low. And when that happens, you get an echo, and that's what the echo is. So this guy is a point. We'll call this point E. And so this was our 180 flip here. And we'll assume that we had done it to point C. So this is 180 flip of C. But we could have waited. And if we had waited, they would have completely spread out into a disk so that there was absolutely no signal at all visible. And then if we just flip the whole disk over, the same thing would apply. So whoever was ahead is now behind, whoever was behind is now ahead. Yeah.
You're saying that ahead, though, returning back to the 1C?
No. So the ahead and behind that I'm talking about is ahead and behind in the XY plane. Yeah. So at the same. So just for the current plan, just ignore the return to the z-axis. That's happening. But the thing that we're interested in is how far ahead and behind are they in the XY plane, strictly in the XY plane. So that's why I'm sort of projecting these guys up, like wherever this guy ended up after we flipped it 180 degrees, I'm projecting it up to the XY plane. And if you look at where it projects up into the XY plane, you can see that the guy, F low now ahead. If you consider the ahead as being this direction, so this is ahead. So basically, F low had been getting behind. So F low, behind. Behind here. This is the ahead direction. So F low used to be behind, but now F low is ahead because they're going in the same direction, but we just kind of flipped them over. It varies, completely varies. Sometimes you do this, sometimes you do this. It just depends on how you're adjusting the timing when you want your echo to appear. So both of these occur. So now if we wait for time, we have to draw time f. So now if we wait for time f, what happens at time f? Everybody comes back into phase. So here's here's what happens at time f. So here's the z-axis and the y-axis and the x-axis. And so what will happen is everybody will all be on top of each other, but shorter, because this thing is T2 decay. So we can't fix T2 decay. So everybody will all end up exactly at the same, because you shoved them under the plane, and so they'll start relaxing back up to the plane. And when they all come back into the plane, all into phase, then you get, and when that happens, that's when you get this big signal. But it still will be decayed. You know, it got decayed by however much time it was after the initial pulse. So it's shorter than this starting, but not but much bigger than it would have been if it had completely decayed away. So this is time point f. Okay, so that's SpinEcho. So it's just a basic thing where you essentially sort of flip the spins around. They still go in the same direction as they were before, because if you do m cross b, it will still cause the spins to be precessing in the same direction. But when you've flipped them around one of these axes, it has the effect of putting the guys who are ahead behind. And by just precisely the exact amount that they used to be ahead. And so then if you just let the same static magnetic field do their thing, then after exactly that same amount of time, everybody will come back into phase. So that's that's SpinEcho. So now what we're going to do is just look at the equations for this amplitude right there. So all we're interested in is like what is that number? Just the middle of the echo, the very middle of the echo. And what does that correspond to? What does that eventually correspond to? It just corresponds to the brightness. So it's just the brightness, of a voxel. So what is we haven't said how we could possibly get voxels out of this because the signal's coming from the whole head, but it's basically just the brightness of a voxel. And so that's what we're writing equations for. We're writing equations for what is, like in an image, what is, how bright is a voxel going to be? Dependent on like how we change the echo time and change T2 and things like that. So I've got this, I have a page of equations, and we'll kind of ignore the fine details of the page of equations, but how do you sort of figure this out when you have something like SpinEcho? Because there's several things going on if we're going to think about this in block equation terms, because there's an RF pulse that's doing something that we could do in the block equation, and then there's some time that occurs for things to get out of phase. That's something we could do in the block equation. Then there's another RF pulse. That's another thing, a third thing we can do in the block equation. And then there's more time after that. And that's the fourth thing. So we have to essentially apply the block equation 4 times. And that's kind of like question 2. That's what like question 2 in the homework is about. How do you sort of calculate what the expected signal would be after you reapply the block equation? So if we do this, also considering the precession, the question 2, you don't have to deal with precession, but if we consider the precession, then we have several sort of transformation rules. So the first thing is the effect, the effect of the effect of an alpha y pulse. So I did an x pulse here, but if we do both of these pulses, just to make life a little simpler, we can do the initial pulse in the, we could flip around the y-axis so that it aims right along the x-axis, just so I don't have to write like a second equation out. So effective alpha y pulse. So here's the transformation rule, and what is that? That just that's a rotation matrix, and so you could write it out either as mx, and so it's a mx prime. So that's a superscript on the subscript. So this means we're in the rotating coordinate system. So we don't have to worry about the rapid oscillation. And so how do we transform the x component of the magnetization? It's the whatever it was times the cosine of the angle, because this is it's basically a rotation. So it's going to be like the rotation matrix minus the y. The z times the sine. And how do we transform the y component? Well, we're rotating around the y, so the y doesn't change. So that just equals whatever it was. And then what about the z? So the z is going to change. So that's the whatever the z was before times the sine, and then that's right, a typo there. Plus last year had a typo in the plus whatever the z. Sorry, this is x z times the cosine. And that's pretty much the same as that our rotation matrix. So you could write it out, if you wrote it out as a sort of a MATLAB matrix, it's the rotation matrix for rotating around y. And what does that look like? You multiply the rotation matrix by the m vector. So that's the full m vector. And what does that rotation matrix look like? It's got, cos, it has like 0 minus sine, and then 0, 1, 0, and then sine 0. Minus cos. I got another typo in it. There should only be one negative. Which one is it? Okay, I know this equation is correct. So it's so here's mx, my, mz. I didn't. Oh, so it's not. It's just in the online notes. Okay, so we can figure out from this correct equation. So this is mx times cos minus mz times sine. That's correct. And so this one is, okay, there's no minus there. Okay. So that's a rotation matrix to rotate something by angle alpha around the y-axis. And so that would be if we did a y-axis flip. So so that's the first transformation rule to help us in our 4 transformations, because we've got a flip, some decay time, another flip, some more decay time. So we have to sort of substitute in 4 times in order to calculate what's going on. So that's the effect of a Y pulse, and now we want the effect of a delay, because we're going to have a long delay there. So effect of delay. And we're not going to go through the nightmare of equations on the page, because I'm sure I would make like 20 mistakes. We'll just have the 3 final answers, which are what we're interested in. So what's the effect of the delay? So now we have to sort of put both the T1 and the T2 decay in. So now what happens is the mx value is equal to the precession. So we've got some precession going on, and so for this we need a rotation around the z-axis, because that's what a precession is. And so this is going to be a different guy. So it's mx prime times cosine of whatever that rotating system, coordinate system is, times whatever the tau time was, in order to figure out what the angle is, plus my prime times the sine of that frequency times the time in order to get an angle. So there's that thing, and then it's going to be decaying by minus tau over T2. Okay, so that includes some precession, precession-like movement. That's what we were trying to illustrate with those arrows moving around in the XY axis. That's occurring during the decay. And then, so this is, this guy is, dephasing, in XY plane. And this guy is, decay in length. And so the X and the Y component will decay in length. So here's the Y component. So that guy is going to be equal to minus mx times the sine of this guy, sine of that guy, plus the y times the cosine of that guy. Also decaying, because that's both the x and the y component decay. And so this, what is this one? This, I won't write it out, but this one is the rotation matrix. You can look, I've got it in the notes written down correctly. It's the rotation matrix if you want to rotate around the z-axis. Because if you rotate around the z-axis, that's changing in the xy plane. So, but that leaves out the z component. So the z component, we have to sort of build in the T1 regrowth. And so here's how you build in the T1 regrowth. It's, mz 0 times 1 minus e to the minus tau over T1, and plus mz e to the minus that initial condition. Okay. The initial condition in this case is whatever we started with. So this thing tells us how we can deal with the actual block equation movement of those vectors. So this is just drawing out in equations what I was just drawing out diagrammatically. So what's happening? We do a flip. That's this thing right here. And then we wait for a period of time, and this, if we apply this equation, it will tell us how to calculate, after we've waited for tau, what the state of affairs is. But then we do a flip, another flip, and so then we have to reapply this to whatever we got after munging mxyz with this one, do another flip, and then we have to take whatever we get out of that and reapply this thing again. So that's the plan. So the plan is, flip. That's this guy, and then decay. That's this guy, and then whatever you get, stick into the flip and do another flip. Flip 2. So here's flip 1, and then stick in again for another decay 2. So if you do that, you just end up with like a forest of sines and cosines and just like a huge mess. But luckily, a lot of the sines and cosines cancel out, and so let's just look at the bottom line. So the first bottom line is the amplitude of the echo. And so what is that? Amplitude of the echo is just this thing right here. So the amplitude of the center of the echo, that's what we're trying to calculate, which, that's why the tau is in there, because tau is the amount of time between like the 180 and the echo, or the time between the 90 and the 180. So the amplitude of the echo is going to be equal to, after doing all those sines and cosines, the mz0 times the sine of the flip angle, of the first flip angle, times the sine squared of the second flip angle divided by 2. So you can see this one is not as useful. It's starting to get a little more complicated. And that whole thing is multiplied by this decay term, which has 2 tau. That's 1 tau and 2 tau. 2 tau over whatever the T2 value of this substance is. Okay, so that's our first. So this is it gets 1 star because this is the most general one. So this is general. So how can we get to e to the minus t over t2, which is what I always, that's what we're working up to. Why do I always draw this? It should be this thing, but that would be way too long to put down. Okay, so now let's consider a special case. So a special case is, special case 1. So special case 1, say we had alpha 2 is just twice alpha 1. So if alpha 2 was 90, if alpha 2 here was 90, then alpha 1 would be 45. So if we just made the second pulse twice as big as the first pulse, that simplifies things. And in that case, here's the second pulse. It's twice as big, but we're dividing by 2, so then it comes out to be the same thing. And so another equation that you might see if you look in an MRI paper would be the amplitude of spin echo is this special case, which would be sine cubed of alpha 1 decayed by e to the minus 2 minus 2 times tau over whatever the T2 value is. So that's a better one, a little simpler. So you often see that sine cubed equation, because if you just arrange to have have the second pulse be twice as big as the first, then it simplifies. But even simpler is, what if we make it 90 and 180? So just go back to sine. So what does a sine look like? So that's what a sine looks like. So if we make it 90, it's going to be 1. And 180, it's going to be 0. But if we just take this equation, if we make alpha 1 90, well, then it's just going to be 1, and so we can get rid of the sign. And so then we end up with the equation that we always write, which is it's mz0 times e to the minus te over t2. And te is just the echo time. So this is, time of echo equals 2 times tau. So that gets 3 stars. So that's the simplest equation for the amplitude. This is the amplitude here of this spin echo. In the special case where alpha 1 equals 90, and it's an important special case because you would most of the time want to do this if you could, because you want to use a 90 because a 90 is going to give you the most transverse magnetization, and then you want to use a 180 because a 180 is going to be twice 90. So this is special case 2. So this is the completely general one that you get from reapplying these transformation rules taken from the Bloch equation in order to figure out what we would expect the amplitude of that signal to be. And then you have a special case if you just make the second pulse twice as big, and then you have a special case if you make it 90 and 180. But that's a practical one that we often use. Okay, so what we're going to do over the next couple weeks is write equations like this, like what's the bottom line simple equation for like what is the voxel brightness that you expect from a particular pulse sequence, or a pulse sequence applied to 2 different T1 values, a pulse sequence applied to 2 different T2 values. So how much of a difference do you get if you assume we've got 2 different T2 values and we apply a particular pulse sequence equation to see how much contrast we can get? I mean, so what you're trying to do here is like sort of rationally design something like how should we set up the pulse sequence so that we get the biggest signal difference between these 2 tissue types. Okay, so any questions at the bitter end? So if you want, there's no mistakes. I fixed all the mistakes on the cosine page. So if you look at the cosine page, a million cosines, how it all mostly cancels out. But just to keep in mind the overall picture of what we're doing. All we're doing is we're just sort of operating the Bloch equation on the output of the Bloch. It's like recursive application of the Bloch equation. So you run the Bloch equation, you get something. Whatever you get, you stick it back into the Bloch equation and run it some more. And then whatever you get, you stick it back into the Bloch equation and run it some more. That's what's going on. You can see it gets quite hairy after a while, and we'll talk. I'll talk in the advanced section next week on how to sort of tame some of the complexity, because obviously if you just talk about 2 different frequencies, you can sort of understand it, but if you've got a whole mess of frequencies, it quickly gets messy. Okay, any questions, last questions out there? Yeah, so remember this one. This is the good one. That's the one I always draw here. All good? Okay, so we'll talk next time. Talk about gradient echoes, different different kinds of echoes.